intelligence for cybersecurity, from anomaly detection to threat mitigation. It's my great pleasure to welcome our today's speaker for the session, Dr. M.V. Pandurangarao sir. Dr. M.V. Pandurangarao sir is a professor at IIT, Indian Institute of Technology, Hyderabad. He has done his PhD from IISc Bangalore, BTech from NIT Warangal, MTech from IIT Kanpur. He has completed totally 38 publications. His first publication is in 2003, that is solving a hidden subgroup problem using the adiabatic quantum computing paradigm. His latest publications are Neural Machine Translation in Low Resource Context Survey, Quantum Network Routing with Heterogeneous Nodes. His research interests lie in quantum computing and communications and formal methods. I request our HOD sir to felicitate Pandurangarao sir with a bouquet. Welcome you, sir. I request you to please continue with the session. Thank you.
Very audible. Yes. Good morning and sorry for the delay.
No.
Sorry about the delay. Because audience is audience.
Yes, sir.
It's our part maybe, but it's the audience. Okay, so welcome to this talk. This program seems to be on AI, ML, and cybersecurity. So I'm not an expert in AI, ML, but I know a little bit about quantum crypto and quantum computing, so I thought I'd talk about that instead. Okay. So I'll do a quick. So it's about a 1 hour talk, so it will be an overview in some sense, and you can ask questions later on. But you can even interrupt me in the middle and ask questions. So I'll use this. So what I would do is I'll first talk about some basics of quantum computing, right? Just the necessary basics for us to understand what comes later on. Okay? So I talk about so a bit, for example, in classical computing is basically either a 0 or a 1. We'll do them. Yeah, it's I mean not much actually. It's either a 0 or a 1. Right? A bit, when you talk about bit in a quantum, in a classical computer, it's either a 0 or 1. Now, if we choose to represent a bit in this strange notation, right, as this vector, right, you could call this as 0 and this as a 1. Right? So, just a strange notation that we decide to follow, a vector notation of 0 and 1. Okay. And if you are now talking about larger system, this is just one bit. If you are talking about n bits, right? In general, a general computer will have not just one bit, right? It will have several bits. If you have several bits, then essentially, let's say you have n bits, right? Then how many possible combinations are possible? 2 to the power n. 2 to the power n. So instead of a 2-dimensional vector like this, we will have a 2 to the power n-dimensional vector. And that is and a description of the computer. So there will be a 1. So if there are multiple, let's say there are n bits out here like this, right? Then how many configurations are possible? All together there are single power n configurations. So a computer, in a very abstract sense, can have 2 to the power n. So we can have n bits in an abstract sense. Even this computer, you can look at it as a very long string of bits. And if there are n bits, you are essentially talking about 2 to the power n dimensional vector, and somewhere you'll have 1. So if it is in that particular configuration, if it is in this configuration, then your vector, suppose your computer is in this configuration, then your vector is all zeros everywhere except this configuration. It's a simple way of but an alternate way of looking at the computer. That's so. Now this is as far as deterministic computers are concerned. You can also talk about randomized probabilistic stochastic machines. They're also it's the same thing, except that you now you have instead of this is also a probability distribution if you look at it. It's just that the probability distribution is concentrated. Probability is concentrated in one point. Right? You can instead say that instead of insisting that the probability be concentrated on one point, I'll have a probability distribution. If I have a probability distribution, my bit will look like this. With 1/3 probability, I am in 0, and with 2/3 probability, I am in 1. So that's some probabilistic function. So I'm slowly leading to the quantum. Again, if you have large computers with n bits, then you will have a probability distribution. Probability distribution always has to sum to 1. That's now we look at the quantum state now. Okay. Just like you have a bit, you have what is called as a qubit, quantum bit. This is these days, luckily or unluckily, there's a lot of press coverage, a lot of quantum computers that's happening. Most of us probably know this already, but I'll just do a quick repetition of what is there. So this is a paradigm of computing which is motivated, which basically seeks to leverage quantum mechanics, some principles of quantum mechanics that are not apparent in the macroscopic level. Right? Macroscopic level, when you throw a ball, the classical physics, the Newtonian physics, etc., is sufficient to explain how it moves and where it falls, etc. But when you go to lower and lower in the scale, you start to see some phenomena which are not there which are not easy to see in classical world, macroscopic world. The question then is that can we do something useful with those quantum mechanical principles, right? So the quantum state postulate is a consequence. It's a consequence of one of the properties of quantum mechanical systems. Right? So the state of a single isolated bit, I'll call it qubit, quantum bit, single isolated quantum bit, this is described by this strange looking thing, which is nothing but this is something that we borrowed from physicists, and therefore we use that notation. When I say this is called like H, okay, and this is nothing but this vector, and this H therefore is nothing but this vector. Just what we saw previously, a couple of slides ago, we saw bit will look like this. I'm just saying that I'm just using slightly changing the notation again, just out of respect for physicists. Okay. So in general, this is a state. It's in general, you can see that it's a linear combination of two vectors. Right? This is a coefficient, constant scalar coefficient alpha, scalar coefficient beta, and this is a linear combination of two basis vectors. Okay. So those who are familiar with linear algebra can see this. And in general, you get another vector which we call as state vector. Okay. Now, quantum, this is the requirement of quantum mechanics that alpha and beta should be complex numbers. Okay, we'll not go into that detail. That's why I said that skips most. And not only any complex numbers, it should be complex numbers such that mod alpha squared plus mod beta squared is equal to 1. What is mod alpha? Mod alpha is the complex numbers modulus. If x plus a plus iota b, it's mod a squared. This should sum to 1. That is the requirement. Okay. And a couple of things that we will use for quantum security. Some of the things, some cryptographic things that we do. Some of the facts that will be useful. One is that it is impossible to clone a qubit, right? If I have, we do this all the time in classical world, right? You copy the value of that is there in one variable to another variable, and so clone this. If what this sentence means is that if I don't know this alpha and beta, you give me this. You just give me. So these are all physical systems, right? These are all atoms, particles, etc. You give me one system without telling me what alpha and beta are and any generic system and ask me to make another copy of it, I will not be able to do one of the principles of. And the other thing is that if two states are non-orthogonal, remember this is a vector. So when you talk about vectors, you can talk about orthogonality, non-orthogonality, 90 degrees to each other, right? If they are non-orthogonal states, you cannot design an experiment which perfectly distinguishes them in the sense that I give you A and B, which are not orthogonal, and ask you to tell me which is which. There is no way I can tell you. I can tell you with accuracy, with perfection. Okay. So now, right? So this is what we are just. So now you can actually generalize this to multiple qubits. You can generalize this to multiple bits, right? Just like for multiple bits, you had this and a larger vector, you can have a larger vector for multiple qubits also. So if you have n qubits, then you have essentially 2 to the power in different combinations, and corresponding to that, there is what is called as the Hilbert space, which forget what it's basically an inner product space over the field of complex numbers. That's a definition is sufficient for finite dimension. We are talking about finite dimensionality. Anyway, so it's a array in the sense that its norm has to be 1, right? And so this, I'm just rewriting the thing in essentially the same notation as what I wrote for a single qubit, right? This is, in fact, instead of alpha 0 plus beta 1, I actually did a summation from 0 to 2 to the power n minus 1, which is the entire collection of vectors. And these are the basis vectors, right? And this is a linear combination of the basis vectors. Nothing fancy still. I mean, at least mathematically, nothing fancy. Again, alpha i's are all complex numbers, and there's some the sum of the moduli is again 1, just like we saw for C. So this basically is a sufficient description for us for uh, uh, of a computer. This has sufficient information until this point. Now, a couple of other things that will be okay. So, a couple of other important things that consider these two states, phi 1 and phi 2. Phi 1 is alpha 0 plus beta 1. So alpha 1 0 plus beta 1 1. Phi 2 is alpha 2 0 plus beta 2 1. 2 qubits, right? If I put them next to each other, can I talk of a joint combined state of this or this? The answer is yes. It turns out that the composite system is described as follows. Okay, which is simply alpha 1, alpha 2. See that alpha 1, alpha 2, alpha 1, beta 2, beta 1, alpha 2, beta 1, beta 2, and 0, 0, 0, 1, 1, 0, 1, all combinations as expected. Right. So this is how we describe composite systems, right? But these are not the only types of systems. These are not the only type of vectors that we will be interested in. In fact, if this is all you can do, then maybe there's not much. There's not much fun, not much fun scope. So here is then what happens is that there is something called entanglement, right? So this is an extremely important resource for quantum computing, and you see in quantum information also, which is basically what is called as spooky action at a distance. Physicists in the 20th century. Right? So the principle is that you create two states, two quantum particles in a particular state, and then send them across very far away. So far away that they're outside each other's life force, in the sense that what you do here cannot affect anything here. At least instantaneously, it cannot affect. Right. So that's something that. So now consider those two particles that I showed. They are prepared in this particular state. 0 plus 1 by square root of 2. Right? And then you send one particle to Alice, A is Alice, B is Bob, and one subparticle to Bob. Okay. It turns out that now the question is, can you so in this case, for example, if I give you this state out here, if I give you this state out here, and I ask you to factorize it into these two states, you can do it. Just separate it out. I'll go on and reverse the multiplication. But so two qubit state, this is a 2 qubit state, and can be decomposed into these 2 single qubit states. This cannot be done for a system like this. In other words, can you always find single qubit states phi 1 and phi 2 such that phi 1 and for this is called a tensor product. You can probably ignore this mathematical aspect, but can you write it as a product? Can you factorize it into two states? It turns out it cannot be done, and this is an example. You cannot probably take it as a homework. You cannot separate this out into two different factorize it into. And this state is very useful in quantum computing as well as quantum information, quantum secure security applications. Okay, so you can do classical gates and circuits. You can just like classical computation. We can have gates and circuits in top of the universal set of gates, just like AND, OR, and NOT are something supposed to be universal classical logic. Similarly, this. So some gates are which we will use control NOT gates. We'll see that. Okay. So the control NOT gate is a specific type of gate. So these gates are, what are these gates? These gates are essentially so till now what we have had is basically a quantum computer, right? By applying these specific types of gates, unitary gates, unitary gates. What are unitary gates? We'll skip that, but it's a specific type of gates that are to be used in quantum computing. So with those gates, you can do various various computations. So the control NOT gate acts on 2 qubits, right? We'll see this, right? Don't get too intimidated by this at this point. The control NOT gate operates on 2 qubits, right? Like this, 2 qubits, and in fact, it's written as this. This is qubit 1. This is qubit 2. This is supposed to be what is called as the control qubit, and this is the target qubit. Okay. The way it works is that if the control bit is 0, then nothing happens on the target qubit. If control qubit is 1, then this is flipped. Right? It's like a flip operation, inversion NOT operation that you see in classical, except that it is controlled by another qubit. That's why it's called control NOT. It's something that we use, like, perhaps in the lecture. That's why I mentioned this. Otherwise, yeah. And then there's another thing called the Hadamard gate, which is also converts this particular qubit into a qubit like this, which will denote as plus, and this as this, which will denote as minus. Right? And if you apply so actually, let me do this for you. The Hadamard gate is nothing but this. This is the Hadamard gate. And if you notice that if you apply it on 0, remember 0 is this, it gives you this. you can do the multiplication yourself and see. On the other hand, instead of this, if this was this, you get this. Okay, and this is exactly what I've written here. 0 plus 1. This is the vector. If you look at it as a vector, this is 1 by root 2, 1 by root 2, and this is 1 by root 2 minus 1 by root 2. That's all I've done. So this is what you get. This is a specific operation called Hadamard operation on the single qubit. We use it. That's why I showed it to you again. Okay. And this is your control knot. These are the only two things that you need to remember for the. One thing is that this is the cloning, no cloning thing that I'm just reiterating some things that it's impossible to clone a qubit. If you have this and let's say 0 sitting here, it's an auxiliary qubit. You cannot copy it like this. Now we are in the position to do one of the first earliest applications in security for quantum. So, what is key distribution? So, I don't know if you have done a session or a course in cryptography. Have you done a course in cryptography? Yeah. So, cryptography, what happens is that you have, and we'll concern ourselves only with symmetric key cryptography. What is called a symmetric key cryptography? Most of us will know about this. The way it works is that there is an encryption algorithm, and which works on this. Let's say there's a machine, there's a message that you want to transmit to somebody. So you and you have a key. Okay. So using this key, you encrypt this message through this encryption algorithm, and you get what is called as, let's say, the ciphertext C. Correct? Right? And how does the receiver decrypt it? He will have a decryption algorithm which takes C, ciphertext, as the input, using the same key, or a key which is very easily obtainable from this. Let's say the same key, and retrieves the message back. Right? This is just standard symmetric key cryptography. Examples are AES, BES, RSA is everything, but AES, DES. So this is a very useful, symmetric key cryptography is very useful because there is something that called as the one-time pad. Right? One-time pad works as follows. You have a message. This encryption algorithm is absolutely straightforward. All you need to do is XOR the key with this, and you get what is called you get a ciphertext. And to get the key back, all you need to do is do this XOR again, and you'll get the message. Very simple. And provided that you change the key again and again. For every message, you use a different key. Okay. This crypto system is actually what is called as information theoretically secure. Right? You just cannot break this. So all these RSA, these, all of this is not necessary. If you can do this, only problem is that every time you need to have a new key. If you reuse the key, then the whole security is lost. Okay. Now, why are we interested in this? We have RSA, as somebody pointed out. We have RSA, TS, and all that. The problem is that something we'll not discuss is in the quantum when the quantum computers, at least the theoretical models of quantum computing came up in the 90s. There was an algorithm called Shor's algorithm, which would actually factorize integers. Right? So suppose given a large integer, which is a product of two large prime numbers. Okay. We still don't know an efficient algorithm. How do you retrieve the primes from there? So if I give you, let's say this n, These are two large prime numbers, and I give you this. Can you give me one of these? That's what's known as the prime factorization problem, integer factoring problem. And it turns out that uh, there is, even now we don't know of an efficient. Of course, we can always do that. I mean, you can always think of an algorithm which is not necessarily efficient, which can basically give you back this even in P2, right? But the question is, do we have an efficient algorithm or not? We don't have. And RSA, the security of RSA crucially depends on the fact that we cannot do this factorization efficiently. The moment somebody comes up with an algorithm which does this factorization efficiently, RSA is gone. Okay? Some of the public crypto systems which depends on problems like this are gone. We don't know of any classical algorithm, but in the 90s, Shor's algorithm actually gave a quantum algorithm that efficiently does this. Okay? So then the question is that if you have uh, algorithms that can break RSA kind of a thing, then what do you do for security, right? Field has so security. So a lot of things have happened. There's this notion of post-quantum cryptography, which essentially assumes that quantum computing is there. Then you do how do you do cryptography and secure communications and so on in the presence of quantum. Once the quantum computers are actually built, Shor's algorithm is a theoretically it's an algorithm, right? Unless one develops a quantum computer, scalable quantum computer, which can actually in which you can implement the algorithm, it will be a kind of safe. But once the day that quantum computer is built, you are not safe. In the context of that, what happens is if you have this is resistant to all algorithms. Forget quantum anything. This is safe. Only problem is distributing the keys rapidly, because for every key, every message, you need a new key. Right? So key distribution among Alice and Bob, the two parties, is extremely important, and very rapid key distribution, because for every message you want a different one, right? So in that context, right? Of course, there are a lot of classical algorithms also for key distribution, right? But some of these classical algorithms again depend on the difficulty of some computational problems like this, right? So what we saw this. So these are some of the key distribution algorithms may not withstand the arrival of quantum computers. So then in that setting, what do you do, right? You can always resort to this. As long as you have a secure key distribution algorithm. You can do even AES and DES, which is kind of still uh, uh, resilient to quantum attacks. You can use AES, DES also. But for that also, you need to have a secure key distribution. Unconditional key distribution, unconditionally secure key distribution mechanism. Unconditionally means it should not be conditioned on the fact that that problem is difficult. So quantum key distribution is a protocol. Is a problem of distributing keys using quantum mechanical principles across Alice and Bob in a secure fashion, right? And one of the earliest protocols was developed by. Let me quickly this. I think I've talked about all of this. Yeah, I've talked about all of this. So one of the earliest key distribution protocols was proposed in 1984 by Bennett and Prasad. Because it was proposed in 1984, and it is Bennett and Prasad, so it's called BB84. In fact, it was proposed apparently in Bangalore. Here for reference. So is the problem statement clear? What is the problem statement? Let me do this. This is important. Problem statement is that you have Alice sitting here and you have Bob sitting here. Somehow Alice and Bob have to agree on a key. Agree on a key means this should be identical to this, because if these are not identical, then your encryption and decryption may not work. You'll get some garbage out here and you'll get a garbage out here. These things have to be exactly identical. And these guys are, let's say, remotely located. This guy is in the US and let's say this is in India. So that's the other. Otherwise, you can always, I mean, if you're in the same room, for example, you can always write down a long string, random string on a sheet of paper and then. Okay, is the problem statement clear? Huh? We're not clear. Not clear? Okay, what aspect it is not clear? Oh, you didn't get this problem statement. So let's say this encryption is done by Alice. And this description, once the message is received, this description is done by Bob. Is that clear? Right? Now, what is necessary? What is necessary for these guys to share? The key. That's clear, right? And this key, let's say this key is 01100111001. This same thing should be here also. For them to do this symmetrically, correct? Now the question is, how do you ensure that both of these guys have the same key? That's a yeah. So okay, so now I quickly run through this BPA protocol. Maybe 10 minutes, 10 to 15 minutes. So the protocol runs at 2x Alice and Bob. Okay. So Alice chooses two vectors A and B of length. I've put this 4 plus delta, and don't worry about this 4 plus delta n. Why this 4 plus delta n? For this purposes of this stuff, you don't need to worry about all of this. Just remember that your final key, the length of this final key, will be roughly slightly less than this, right? If you want an n-bit key, roughly an n-bit key between Alice and Bob, then you would want to choose 4 times it to begin with. At the beginning of the protocol, you have to choose 4 times. That's all I'm saying. And obviously, this key, the longer this key, the better, right? Because if it's a short key, then people can guess it, right? You can cycle through. Let's say it's a 3-bit key. I'll go from 000 to 111. I'll just. That's not interesting. You need to have a large key because the key space then becomes 2 to the power n. Right? So that's what we call. Anyway, so Alice chooses 2 bit vectors. Right? I should probably put a hyphen here. It's not a 2-bit vector, it's a 2-bit vector. Okay. Called A and B. Right? And each bit in the above 2 vectors is chosen by tossing a fair coin. Essentially, they're completely random vectors. A and B are completely random vectors. Okay. Your guess is as good as mine as far as guessing these 2 vectors are concerned. I will not be able to reproduce this vector in any manner. Right? So this is a quick sneak peek. A small part of A, roughly of the order of n, will be the final key. Right? This is a random string, and as part of that random string will eventually. Let's see. Let's go back, go a little forward, and then we'll see. Right? So now, this basically, so he chose, Alice chose 2 vectors, big vectors, A and B. Right? Now, this B is something, this B is a vector that will allow you to choose how to encode qubits corresponding to vector G. Right? Roughly, intuitively, we'll see exactly how it is done, but I'm telling you upfront a little bit. So depending on what the value of the ith bit in B is, Alice will choose the basis. What are the bases that we are talking about? The basis that we are talking about is, I'll tell you, is this. Remember, I talked about two bases out here, right? If you talk, this is a basis for a two-dimensional vector space. You know, all basis we all know, right? Set of linearly independent vectors that spans the entire space, right? So this, if you want me to write it pictorially, this is the basis, right? This is basically 0, and this is basically 1, right? This is 1, 0. You can see, remember from your 10th, 12th standard Cartesian geometry. This is 1, 0, and this is 0, 1, correct? Yes, no? Right? Yes, yes. Now, what I'll do is I'll take another basis, right? I'll take this basis. This is also an orthogonal basis, 90 degrees basis, and it's also a legal basis, right? Because it spans the, you can write any vector in this two-dimensional space in terms of these two vectors also, right? This is basically, I'll call it as 0 plus 1 by square root of 2. By square root of 2 is because of that all of them mod squared has to sum to 1 and so that's why this is the mod square root of 2. And then this is basically 0 minus 1 by square root. This is clear. Maybe if you use a different pen. Okay. Clear. Is it clear? These two bases I'm talking about. Now, if Alice wants to send the qubit to Bob, okay, she can send it like this, encoded as 0, or encoded as 1. Not just that, she can choose a different basis and send either a 0 plus 1 by square root of 2 or send a 0 minus 1 by square root of 2. She has 4 choices, right? First is basically she chooses which basis. Should I choose the green basis or should I choose the black basis? Right? Huh? She is up to her. She can either choose the green basis or she can choose the black basis. If you choose the green basis, she can choose either 0 or 1. If she chooses the black basis, she can choose either 0 plus 1 or 0 minus 1. Prepare the qubit in that state and send it across. That's the simple. That's the basic thing. Right? So depending on what value of the ith bit is, ith bit in B is, if it is 0, she choose the green basis. If it is 1, she choose the black basis. That's what this sentence means. So, and in this manner, this is an example. Okay. So if Bi is 0, then she chooses the green basis. And the ith bit of A is 0, then I'll send 0. I mean, Alice will send 0. Similarly, let me complete this and then we'll exactly do this. Right? If green basis is chosen and the ith position is 1, then we'll send this. If ith bit is 1, so BI is 1 and AI is 0, then it sends plus. Plus is in the black basis, this I call it plus. I showed it in a previous slide. This is I'm calling this as plus, and I'm calling this as minus. Sorry, black basis, right? So that right in black. This is plus, and this I call it minus. So based on this, she essentially bottom line is that she, in some random basis, which is decided by B, she sends a random encoding, which is either 0 or 1 or plus or minus. This is what she sends to Bob. Okay. At least roughly it's clear what's happening. Now, when Bob receives this, what happens? When Bob receives it, what essentially he can receive is one of these 4. Either he'll receive this, or this, or this, or this. right? Based on, well, these are, well, maybe I should use correct color. It should be black. Obviously, none of these four, correct? So now what happens is, here is what actually there's a, we can do it mathematically, but it's probably easier to imagine it in more intuitive terms. Think of it as those, so I don't know if you have seen this polaroid crystals in 12th standard they used to teach. Tourmaline crystals, right? So you see in one, the light is cut by half, and then you put another crystal, and then when you rotate it, it becomes from bright to dark. In fact, it becomes completely dark. If both the crystals are aligned at 90 degrees, becomes completely dark, right? So, in other words, so now notice that Bob knows nothing about uh, what kind of basis she used, what kind of qubit she's used, nothing. There has been no communication between Alice and Bob, except that he has received these bits, these qubits. He has received these qubits. Now what he does is he has that crystal kind of a thing, which he rotates randomly and starts measuring. Okay. So what can he do? He can say that. So there are, as far as the crystal is concerned, there are only two directions, two bases. One is the green basis, you can tilt, or you can tilt in the black basis, right? If it is in the green basis, let's say he tilts his equipment in the green basis, then what happens is that there is a basis match. You do this, he does it, he measures the incoming qubit in this basis. There's a basis match, and he will correctly conclude that this is actually zero. Because the basis is matching, right? So this part needs explanation. This part needs a little math also. I'm showing it in an intuitive fashion, right? Similarly, in the same basis, this also is okay, no problem, because the basis is matching, it aligns with this, and therefore it will see a 1 even for this. Correct? That's kind of intuitive, right? Because the basis is matching, either it is aligned like this, no problem, or it is aligned like this, no problem. The problem comes when he uses this basis, but the incoming qubit was this. If the incoming qubit was this, then with some probability it will say 0, some probability it will say 1, no, nothing, we can't get inconclusive. The fact that I mentioned the fact that you cannot distinguish non-orthogonal states reliably has a role to play here. The fact that in this basis you cannot measure this with confidence plays a role out here. So if he is using this basis and this comes, then also there's a problem because the tilt is in this direction, right? On the other hand, if he decides to measure in this cross basis, I should use the green thing. Let's say this is the green thing. If I use in cross basis, then these two, this will not have a problem because they are aligned. Similarly, this also will not have a problem because it's aligned in the other basis vector. No problem. But if this you are measuring in this basis and this guy comes around, then there's a problem because they are not aligned. Similarly, same thing with here. So she gets a bunch of results, right? Some of them are wrong because of the fact that they didn't match. Some of them are right, right? So then at this point, what Alice does is she says that, okay, fine, I will announce what all bases I used on public channel. I can pick up a phone and tell you, let people listen on the phone, no problem. Right? It's not a private channel, it's public channel. Also, classical channel, the phone, temple phone. So she'll say that for the first position, I used the black basis. Second position, I used the green basis. Third, also I use green basis, green, black, etc. Okay. Now, once this guy understands that she has used these bases, he knows exactly which of the bits he has to discard. Right? Wherever she says, let's say she says in the first position, let's say I use the plus. If this guy also use the plus, then you will say, yeah, good, it will work. On the other hand, in the second basis, let's say she says that I use the cross basis or the green basis, the cross basis. I call it the plus basis and cross basis instead of green and black. Right? If she says cross basis, and it turns out that this guy used the plus basis, then he knows that I am in trouble as far as this position is concerned. So I'll drop this bit. I'll drop this bit completely. Right? If there are 4n bits to begin with, how many bits do you think will survive this process? How many bits will survive? So this guy has also chosen his basis randomly only because he has nothing else to rely on. He is also using it randomly only. What is the how many bits will it survive? Out of 4n, how many will survive? Yes. Huh? No. Why one? One of them is right. One of them is right. So see, no. So basically, no. So okay. So you want? So I'll tell you. So right now we are talking. Right now we are talking about random choice of basis, right? So this guy is Alice chose this basis randomly to send the qubits. She chose this basis. This guy also chose some bits randomly, right? They will drop those bits, those qubits, which do not match, where the bases do not match. They will drop those qubits where the bases do not match. My question is, if there are total 4n out here, how many do you think will survive this process of dropping the mismatches? No, roughly 50%. Correct, exactly. Roughly 2n will survive. Out of 4n, roughly 2n will survive because the bases match. Okay. Now the thing is, actually the quantum part is over at this point. The quantum part is over at this point. After this, what happens is some classical discussions happen. So yeah, so we have seen this. So he chooses between 0, 1 and 1 with this basis or this basis. He chooses by tossing a coin. Bob also does this. Now analyst announces B, the basis vectors. Right? In what basis I chose the sequence of basis Alice announces over a classical public channel. Alice and Bob discard the qubit for which there was a mismatch of basis choice. This is expected to happen for about half of the qubits. This is very important. This is very important for the following reason, right? This is about half with slight margin of error. Let's say you can be 5% here or there, and this can be shown with a very high probability. Uh, why am I particular about 5% or 5, 6, 8, little bit only? About half will survive. About half of the time they'll match. The reason is that and that's a statistically proven thing. One can actually prove that with very high probability, the disagreement will not be on more than small number of places. This is a statement that you can prove mathematically. What is a statement you can prove? With very high probability, it's also again a probabilistic statement. With very high probability, the difference between the basis choice here and here will not be more than, or will not be significantly away from 2n in both directions. It's roughly and by half of them will drop. The reason is that if there are more discrepancies than half of them, right? So what happens is that at about 50% of the time places there is agreement, and they decide to keep the qubits at those positions. Wherever there is agreement, they will keep those positions because we saw that, right? If this was sent and this basis was used, I would correctly interpret it 0. I have actually securely retrieved 1 bit of the key from Alice. Similarly, here also, if it matches, here also it matches. I have another bit, right? And so essentially, about 2n sized key I should have ideally, right? Is that clear? In all of this, one of the important things is secrecy. If I have, if I have a 0 here, we have actually converged on a 0 for the first position. It should not be known to any other person, right? What we have to worry about is the presence of an eavesdropper in the middle. Okay, because of some of the principles of quantum mechanics, which we will not go into, Eve cannot disturb a lot of qubits without getting detected, right? Because of that it's a consequence of the fact that you cannot measure you cannot distinguish non-orthogonal states perfectly. Therefore, that's a problem for eavesdropper also, because quantum mechanics gives this problem to eavesdropper also. Because of that consequence, let me just state the fact. Because of that thing, the consequence is that Eve cannot disturb too many of these qubits without getting detected. So if it turns out that I'm expecting to drop about half of the qubits because of the basis mismatch. That's purely statistical thing. Half of them will not match. But if Eve is there, eavesdropper is there, what will happen is her activity, if she tries to tamper the quantum channel in between, her activity will introduce errors, which is more than the 5% tolerance that I had booked, that I am prepared for. So instead of 5%, so 50%, so for half of them plus, let's say, some 5% is something that's acceptable to me. If the interference is more than that 5%, whatever the threshold is, if the mismatch is more than 5%, so I see that, and so then what happens is the next part is this, right? I have to come to, let's do this, and then after this whole process of basis measurement, basis comparison, all of it done, right? What happens is some things survive here. 0, maybe this goes, then 0, 1, 1, 0, 1, 1. Correct? Similarly, here also 0, 0, 1, 1, 0, 1, 1. This should survive. Right? There are about half of them. If there are 7 of them, maybe these are 14. Okay. Okay. That's. I think, is this visible at the back, or you can come to the front? Some of you. I don't need too much of. Much more time of blackboard. Is it visible now? Right. So So ideally this should happen 001, 1011, 001, 1011, half dropped because of basis mismatch. I'm left with half, right? Now, is this clear, right? Roughly half of them are left. Now what happens is, um, let's say there is channel error. Channel also is not perfect, right? Quantum channels means you are ultimately you're talking about optical fiber, free space, and so on, right? Yes. So what will happen is some things, although everything was done. So for example, so this in this basis a qubit was sent. Bob also measured this in this basis only, and he should get this 0 because it's in this direction. 0 he should get. But unfortunately, channel did the mischief. Channel mischief in the sense channel had a problem, and channel flipped this to, for example, this, for example. Right? That's not in our control. It's a fiber optic channel. We could do it. In which case, what happens is this becomes he'll actually see a 1 instead of a 0. Right? Correct. Yes. So he has to account for this now. We have to account for this. So what we will, in other words, what happens is, although this was sent as 1, maybe this was received as 0. Yeah. Among the remaining also. Among the remaining, this was sent as 1, but this was received as 0. Right? Clear. Now, if we know the characteristics of the channel, how the channel behaves, right? We know that another 5%, another 5% there will be a mismatch, right? Because that's how my channel is. I know my fiber optic, I know its characteristics very well. I know that there will be some mismatches, right? So what they do is to eliminate. So I'll come to that later. So what they do is they choose some 50%. Right? This was 4n, roughly 4n. This dropped to 2n. Okay. Out of this 2n, what they'll do is they will say, let's compare. They'll say that let's compare the values at some half of these positions publicly, again on phone. Pick up the phone, compare the first value, match, no problem. Pick up another random value, not necessarily the second only, some random value. Pick up this value, for example, next. Next, this value also match, right? This value, no, there's a mismatch. Similarly, you do it for 2n, half of these you do. The expectation is that if knowing the channel, you know how the channel works, and so therefore you would expect out of n, maybe some small number of mismatches. Out of the n that you discussed over publicly, some n mismatches have happened, which is again fine. If it's within a small tolerance of again some 5%, we are fine. Right? If it's 5% of the publicly declared bits mismatch, it's okay. Because of the fact that the channel behaves in a certain manner, we can't do much about it. Roughly, this many we are expecting, and therefore then I'm fine. However, if the eavesdropper is eavesdropping, right? Because one has to show a little bit of calculation. If he does too much of eavesdropping, right? If she does one, it's okay. One bit here and there, it's okay. If she does too much of eavesdropping, then what will happen is that there will be necessarily a lot of mismatches here among the compared things also. Publicly compared things, there will be a lot of mismatches. At which point they abort. They said that look, something funny is going on. From the 2n bits we had, we compared some random half of them, some randomly chosen half of them. We were expecting these many mismatches because of we know the problem. But now there are more problems than this. The mismatches are, out of 100, I was expecting, let's say, 6 mismatches. It turns out there are 25 mismatches. Surely something is wrong. And then they abort the program at that point. On the other hand, if only 6 to 7% are mismatching, they know that it's okay. Either Eve is not there, the eavesdropper is not present at all, or the amount of tampering that she has done not it's within control, right? And Alice and Bob compares the value of these check bits. These are check bits. If the number of mismatches are more than a threshold, then abort. That's what we discussed. Otherwise, what you do is what happens then? Suppose we decided there's no, let's say only 5% mismatches were there. Okay? Only 5% mismatches were there. If there were 5% mismatches in the publicly announced N over 2N, what is the how many mismatches would you expect in what you did not announce? You chose randomly out of this 2N, you chose N positions and actually compared the bits. So they're all almost the same except 5%. In the remaining that we did not discuss, which is supposedly secret between you and Alice, how many mismatches would be there? Again, about 5%. Because there's nothing to discriminate between what you were announced and what you did not announce. So the announced had 5%. So most probably you will have about 5%, again plus minus 1% or so. You'll have it in the thing that you did not announce. Now, discrepancies are not allowed. We want exactly the same key, right? So 5% discrepancy, which probably because of the channel, that discrepancy, the mismatches have to be eliminated because you want exact same key out. How do you eliminate it? You eliminate it by a series of what are called as parity checks. You would have probably know parity check. You have a string, you compute the parity and check their whether they are the same. Not just one will not have will not be sufficient. You'll have to do several parity checks. There is an algorithm which is called as information reconciliation. And this information reconciliation, these parity check comparisons happen on the public channel on the phone. Now, because of that, what might happen is that some information might leak out about the secret key that was never announced. And to prevent that, what you do is you do what is called as privacy amplification, and which is again basically there are many ways of doing it. One way of doing it is using your standard hash functions, uniform family of hash functions. Take some hash function which basically compresses the key, and you get some m which is less than slightly less than number of keys, number of key bits. So then that becomes a secret key. Information reconciliation, I'll probably skip this. Do a sequence of parity checks out here, and then the privacy amplification is done using the hash function. I'll probably skip the rest. The important part is what we discussed over there. So some conditions on the cycle. Okay, so it's 12:25. So there is another thing. This would have involved the entanglement that I talked about, but probably we could stop here. In the interest of time. So I'll stop by taking a minute of recap of what we did. Here, you start with 2 bit vectors. Alice starts with 2 bit vectors. One decides the actual key. The other is for basis choice. She encodes the qubits on the basis choice, which is also a random bit. random bit vector, sends the qubits out here. This guy also chooses his basis randomly and measures. Because these two bases have been chosen randomly, they will only agree at about half of the places. Alice declares her basis sequence publicly. This guy sees that there was a match. Wherever there is a match of the bases, he keeps those bits. Wherever there is a mismatch of the bases, he drops those positions, those two bits. Then, to uh, 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 roughly half of them survive, right? Because these bases were chosen at random, roughly half of them survive. From here, um, to further do a further check, out of out of 4n it falls to 2n because of base mismatch. In this 2n, they select some n of them randomly and compare them. Actual bits they compare. Do I have a 0 here? Yes, I have a 0 here. Do I have 1 here? No, I have a 0 here, and so on. See if there are too many mismatches. If there are too many mismatches, they abort. If the mismatches are kind of within the tolerable level, then they will go for the information reconciliation protocol, where they seek to uh, make these through a sequence of parity checks. They seek to make this. They make these match. During this discussion, some information might leak out to eavesdropper. So they do further privacy amplification thing, which basically makes it secure. Pretty secure. This protocol, if implemented ideally, the implementation is another problem, right? You need a lot of technology, you need single photon devices, single photon detectors, etc., and so on. So a lot of this thing. But if it is implemented faithfully, this gives you a very uh, uh, secure way of distributing keys, which does not depend on any the computational hardness of any problem, and therefore it's secure. So there is a lot of work that is done also now in the implementation. So there are devices, quantum key distribution devices that are available off the shelf. You can buy it if you have a couple of crores or maybe more. But it's a very fairly mature technology. And yeah. I'll probably take a couple of questions instead of going on to teleportation. Some questions. Maybe I'll take 4 minutes to quickly tell what the teleportation is. Okay, so that so basically, let me actually, instead of this, what I'll do is I'll probably put it on the board. So again, same Alice and Bob. Alice has a state, quantum state. Okay, that's fine. Alice is a quantum state, and um, and a classical channel, a telephone line with Bob. Okay? And as Bob is very far away, right? So far, I mean, it could be a different planet also, right? And she wants to transfer this state from here to here. Somebody has given this state to her, and she has said it and has told her to transmit this state to Bob. They have nothing else except this telephone line and what is called as this tangled pair that I have mentioned. Right? At some point, they were in the same laboratory, so they created this state of 2 qubits, a pair of qubits in this state, and she took one half, and this guy took one half of this pair. Right? One part of this particle of this pair. Alice took one particle of this. Bob took. Other than that, they don't share anything. This classical channel is there between them. And the problem is to transmit this state vector to this. And in that sense, it's teleportation. So as those who have when some of the science fiction things started, kind of thing, a person disappears here and appears here. Right? That's teleportation. You're not talking about people, but you're talking about quantum information, one qubit. Magically, basically, it can be made to disappear from here and appear out here. Magically, in a sense, because of quantum mechanics. There's this classical channel also you're sharing, and this EPR pair also sharing. You do some operations on this side and some operations on Bob's side, and suddenly it appears out here. The protocol which accomplishes that, and it's a very useful protocol for various things, in particular communications, secure communications. And just skip all of this. There's some. This is slightly old actually, few years old. So just to show a picture of some of the equipment that are used over. So this is something that you can actually buy from this company called ID Quantum and so on. And there are many other companies. Now India itself has companies which does teleportation also has been achieved over long distance, not really, but long distances. So yeah, I think I'll stop here. Any questions? Please, I'll be happy to take questions. Feel free to ask any question.
Although it is a bit tough topic to understand, we are not into this. Just statistically, it behaves statistically. So, what is the credibility of the accuracy of this entire mechanism?
That's a good question. So what happens is that so what essentially you're asking is how do you prove that this is secure and goes to this, right? So for that there is you show that it is information theoretically secure in the following sense. If there is a bit and if it's sitting in between, right? Then the information gain that she has, or let's say the mutual information. The information is the information theory, right? Information theory, coding theory. There are this notion of entropy and so on. That's so. So one shows that the eavesdropper gets, if the protocol is executed properly, the eavesdropper gets exceedingly low information about what is going on. It can prove the number of bits that you get, that an eavesdropper can get by eavesdropping and doing whatever she wants. Right? You can assume that she has access to a quantum computer herself, right? And unlimited amount of classical computing, etc. Whatever you want to assume, you assume, and still the amount of information in actual sense, in the number of in terms of the number of bits that she can pull from here is exceedingly low, and therefore with high probability, and therefore it is simple. So how do you prove such a thing? You start with a very simple yet information theoretically secure protocol, right? So that's it's a simple protocol where one can show from principles of physics. This is one way of showing it, by the way. I'm not saying that this is the only way of showing it. One way of showing it is that, so you assume that Alice and Bob share what is called an EPR pair, the zero, this one. Alice and Charles, this thing. So one property of entanglement is that this EPR pair is that if Alice and Bob, so one particle is with Alice and another particle is with Bob. If Alice chooses to measure what she has and she sees a 0, then physics says that he will also get a 0. If she sees a 1, he will also get a 1. Right? A very simple protocol, therefore, would be to have a bunch of these particles, these systems. Let's say some n of them. And do this again and again, so they'll actually get an identical string. Second bit, third bit, an identical string. And it can be easily shown because of the principles of physics that this is completely secure. Assuming that you have a state which is looks like this, right? Then it can be shown that this is fully secure. Problem is if there are any problems, simple implementation detail, how do you keep distributing it, and so on. So many problems. Now what they do is, one way of showing that your BB84 protocol is secure is that dilute this protocol from requirements of this entangled pairs, etc. Dilute this protocol step by step, without compromising the original security at any point, right? And therefore, you dilute this and get it down to BB84, the protocol that we just discussed, without having compromised security at any point.
So this iteration will be followed when the threshold is not.
No, this is a proof. This is not a protocol.
Okay.
You want to see that this protocol BB84 is secure. How do you prove that BB84 is secure? You first prove that this protocol that I just now mentioned is secure. You first prove that, right? And that is easy to prove because of various laws of physics. This is easy to prove. Now what I do is I modify this protocol a little bit, but I show that nowhere is the security compromise. Modify it again, modify it until we reach this BB84. So I have done these modifications and gotten this protocol, but at no point have I compromised on the security, and therefore BB84 is. That's a way of proving. There are other ways of proving. You have multiple ways of proving. So to answer your question, it's the proof of why this works and why this is secure. The argument has to come from information theory. Any other questions?
So with the limited knowledge what I have about quantum computing, I'm just curious to know. We know that, like for example, simple addition, I want to do quantum computing. That's but whereas if I take a multiplication, quantum computing goes down there when compared to what the traditional computing is doing. Is there any such pitfalls in quantum cryptography also?
Can you say the first part of the question?
It's like, as of the knowledge I know, quantum computing is not like we can use it in all the applications. So there are few applications where it's giving us really good results, whereas there are certain applications where the traditional computing is giving us faster results when compared to. So similarly, is there any such pitfalls when we talk about quantum cryptography?
Not really. At least in what the protocols that I mentioned, there is no such pitfall. Only pitfall is that you faithfully implement this. Your hardware, your optics, etc. should be such that it faithfully. What do you mean by faithfully? For example, if I say that I have a state. So what can happen? For example, I'll give you just one example of the top of my head. So what happens is that these things are sent in a pulse. Okay, these qubits are sent in a pulse. Inside this pulse, we will decide the qubits, the photons, right? Now, if there are, let's say, several photons of them, I'm kind of using slightly ambiguity and colloquial in this thing, but this kind of tells you the essence of what I mean by faithful implementation. So there are several photons in there. Now, what happens is you can close some of these photons and let the pulse go, right? The guy there was expecting one photon. He'll get the one photon, despite of the fact that she has actually pulled out some photon that she's now using. So the trick is to basically have just one photon, if she takes off, that way can do. Those kind of implementation details and care has to be taken. Other than that, any other questions? So I'm sorry, I have to run. That's why. Otherwise, I would have 3 minutes.
Thank you so much, sir, for your thought-provoking discussion.
Okay.